Okay, thank you, Leo. All right, so welcome back early in the morning. And so my first two lectures have been fairly abstract on the theory of spin liquids. Try to bring you up to date on, you know, rather remarkably complex developments on just the simple issue of what are possible spin liquids of the square lattice, which are close to the Néel state. But I think there's been some very beautiful progress, and now we understand enough that we can, with some confidence, try to extend that to the doped case, and that's what I'm going to talk about today. But I'll begin with, and many people have been asking, what is this pseudogap? So I'm going to review some key properties of the pseudogap, and then a little bit of history, and also tell you where we are today. Okay. All right, so the pseudogap is this particular region of the phase diagram. I can look over here, which is above TC on low doping in essentially all of the whole doped cuprates. And it's also above where there's any appreciable order that's observed by X-ray scattering, neutron scattering, or so on. It was initially discovered by NMR measurements of the magnetic susceptibility. So if you lower the temperature in any kind of metallic state, you get a Pauli susceptibility. And so that would mean, and that's what happens down here. If you come down this way, the susceptibility is roughly constant. But when you're over here, around this temperature T star, it starts to go down. Doesn't go down exponentially fast, but it starts to go down in a way that, that people do. I don't know who used the word pseudogap first. It could have been Henri Ellul, who discovered it in NMR already way back in '89. But I'm not going to talk about that property so much, although it's implicit in the description I'm going to give. But focus on two properties, photoemission and magnetotransport. So if you do photoemission, and if you're on the overdoped side, so if you're over here in this region, then you see a beautiful Fermi surface. So the electrons are in this region, and the holes are here. And if you just compute the area, it agrees very well with 1 minus p electrons or 1 plus p holes, where p depends on this delta in this particular material over here. All right, so that's great. That's exactly what density functional theory or any kind of perturbative method would tell you. So it gives you some confidence that we have identified the right microscopic degrees of freedom. Also, if you look away from zero energy, so this is the spectrum at zero energy, which is where the Fermi surface is. If you go away and look at electron and hole excitations, you just see one band. There's just a single band. Now that band may be kind of complicated. It may be the orbital is partly on the oxygens, partly on the copper. We don't know. But no one's ever seen more than one band in photoemission. In other materials like the pnictides and so on, you see plenty of bands. But here, there's only one band. I want to emphasize that because many theorists work with 3-band models of copper and oxygen. That's fine. I have no problem with it. That may give you, that may be useful to describe, the Hamiltonian that you need. But the final Hamiltonian that you need, I believe, should be a 1-band model. Because you never see anything else. And then you have to do a projection from 3 bands to 1 band, and that may change the form of the Hamiltonian. I'm perfectly okay with that. Okay. So I'm just going to work with a simple 1-band model. Okay, so if you take this system and you underdope it, then you get the arc. So what you see here is that this large Fermi surface has been cut off in these regions, which are called the antinodal regions. And so there are no zero energy excitations here. So that, if you wish, is the gap. There's a gap here, and this is well above superconducting temperatures. And these are sometimes called the Fermi arcs. So this is rather mysterious because there's no, in anybody's theory, there's just no way to get arcs. You can get, close to the Fermi surfaces are always closed because you're solving one equation for the pole of the Green's function, and it's going to give you a closed curve. It can't just disappear. Okay, so that's the big mystery, one of the big mysteries. What are these famous Fermi arcs that you see in photo emission? Then you can also look, so here's another picture. I guess I missed a slide. Anyway, so this is the same Fermi arcs, but let's look over here. So now you look over along this direction. You scan in momentum along this direction, which is this axis here. And you look at the dispersion of where the maximum scattering is. So in other words, there's some particle-like object, which is somewhat broad, but anyway. So there is a quasi-particle excitation, and look at its energy. So if you're at high temperatures above T star or at high doping, you get this red line. So what you see here, the red line crosses 0. So these are the Fermi points. And what are these 2 points here? Well, they're these 2 points over here. If you scan this way, you get a 0 energy. So this point here and this point here are these 2 points in the red. Okay. In this case, this is the same sample. You just gone above T star. But now you lower the energy, and then you get this blue curve. So now there's a gap. The lowest energy excitation of an electron at the Fermi, what was the Fermi vector, has opened up a gap. You've gone from the red to the blue as you lower the temperature, and there's your gap. And this gap represents the absence of any intensity over here. Okay, so that's the magnitude of the gap in the electronic spectrum. It's about 40 MeV, 30, 40 MeV, which is quite a large energy. This is not a small effect. Yeah.
So I'm wondering, just to be devil's advocate, there's always a resolution, there's always temperature.
Sure.
Could it be that it, quantitatively looks like this, but qualitatively there's a very small weight?
Well, this is a intensity plot there. So whatever the weight that is, it's so much weaker than anything here. You can see.
Sure. So there's still something to explain.
Yeah.
As a qualitative thing, it could be just below the resolution of the experiment.
Okay. Fair enough. Yeah. So that's a limitation of photo emission.
Of course.
Yes. Yeah. So one point of view, which I will review, is that really it's a full Fermi surface, and because of, I don't know, some fluctuating order or something, some kind of fluctuations, it's kind of faded away. Okay. That's a valid point of view, and many people have taken that. I'll talk about it. Yeah.
Faded away meaning Z is strongly angled.
For example, yeah. But if you now, on the other hand, if you sit at this point where the Fermi surface was, I don't have those plots here. There's like a zillion plots in this paper, so please have a look from Stanford. You can go this way. You can sit at this point and look as a function of energy. And then as a function of energy, you see a peak, okay, which you would never see on the overdoped side. You see a large peak. And this is the position of that peak. So there's definitely something here which has a gap, which gives you a large peak in what's called the EDC, the energy distribution curve. There's a peak. So there's some excitation that's gapped. There may be also, maybe there's something at the Fermi surface too, but it has a very small Z. But the fact that there's a gap full excitation, which is actually distinct from the superconducting gap, is very clear in the data. In fact, this green line is below TC, and that's the superconducting gap that appears below TC. Yeah, this data is very confusing. But slowly I'm starting to run. But it's a beautiful paper with all kinds of plots, all there for you to look at. When I have heard ZX give this talk, I didn't understand a word of what he was saying. I had to go back and look at the paper and really sort it out myself. But hopefully I made it clear. Yeah.
So just a historical question. You said people saw NMR in the 90s, 89.
Yeah.
What happened between 90 and 2011?
Well, I think photo emission, there was really, I mean, the improvement in technology in photo emission is remarkable. There was no, you couldn't resolve this, have any photo emission data of this resolution at that time. Yeah, I mean, photo emission has become a completely different ballgame since the 90s. Yeah.
Well, they started these EDCs, right?
Yeah, I mean, and yes, thanks. Yeah, that's right. They had these completely new spectrometers, the resolutions and everything. It's just, it's totally different. Yeah.
Below TC, does one see both the green and the blue modes?
Yes, yes. Yeah.
The green mode just appears as you go below TC.
Yeah, yeah, that's right. So that's believed to be the super. So this also shows very clearly, if you look at all the data, that the pairing gap and the pseudo gap are totally different.
That's really weird. I thought superconducting gap was a lot smaller than the pseudo gap.
This is at the antinode. I don't know. Yeah, I think.
Here it looks comparable, but
Yeah, I was looking into the paper on exactly that point because it bothered me too a little bit. Well, I mean, it is, so, this is the gap at a finite wave vector. If you compare the superconducting gap with the pseudo gap at pi 0, that's here, that's much bigger. That's 60 MeV. I mean, the pseudo gap comes down, but at a non-zero wave vector.
So what does negative energy mean?
Hole-like excitation.
Sorry.
Yeah. I mean, that's the only thing you see in photo emission. You knock an electron out. Yeah.
If you want to go on, you should. But if you follow the blue mode around the Fermi surface,
Yeah.
so presumably it goes down in energy as I go towards, the arc.
You mean this way? So you want to sit here and go this way?
That's right.
Yeah, I'm not sure what happens. Yeah, I'm sure it's in the paper. Or you may have to put together 10 different plots to figure it out. Yeah, we can look at it. Yeah. I mean, the data in photo emission is 4-dimensional. You have intensity versus momentum and 2 frequencies. And just taking different cuts is already a complicated task. Yeah.
I thought RPES can only detect states below the Fermi.
Right. So these are all below. What's this? Yeah, they have some trick from you. They look. There's a Fermi function, and they deconvolve it. So of course the reliability goes down. But, yeah. Yeah.
How should I understand like the discontinuity in the blue dots?
I don't know. I think they just didn't have the right data there. Yeah. I don't think it's a discontinuity. It's just very steep, so it's hard for them to get points there.
Okay.
All right. So now another probe, which is magnetotransport. And this is much more recent. And this has started to give a very different point of view. And that's really the heart of the problem. But this is just 3 years ago, paper by Brad Ramshaw and Louis Taillefer and others. And what they're measuring is what's called ADMR, angle-dependent magnetoresistance. Well, what you'd love to do, of course, is to sit in the pseudo gap and see quantum oscillations. I mean, just sit here and do quantum oscillations. Unfortunately, and I'm sure they've tried, the samples are too dirty, the fields required are too high, and so on. So no one's seen quantum oscillations at high temperatures. People have seen quantum oscillations down here, and that's a whole different story, but I don't have time to talk about that. But it's in the notes. Okay, so what the best people have seen from magnetotransport is what's called angle-dependent magnetoresistance. So you take your field and you tilt it at some angle. And so quasi-classically, if there's some Fermi surface, the particles, the electrons are going to move around in this orbit in momentum space around the magnetic field. And then you write down a Boltzmann equation with some kind of impurity scattering, which you then solve, which the experimentalists solve, around this of the motion of the electron around this orbit. And from the solution of the Boltzmann equation, it's basically semi-classical. You just write down the equation of motion in momentum space. dk dt is v cross b minus v over tau to give you the relaxation. And then you compute the c-axis resistivity. So what you measure is the axis resistivity in this direction as a function of angle. Yeah, that's all angle. All right, so if you're on the overdope side, so if you're over here, here, then what you see, that's the left panel, so P greater than PC. So this is the data as a function of angle, and even for different, I think phi is the direction in plane, and theta is the direction from the c-axis. So you get various curves in the experiment, and this is the theoretical plot obtained from some presumed Fermi surface. So if you take a large Fermi surface, you can see it gives an excellent fit to what's going on. So again, no surprise. We already knew that from photo emission. Everything works. OK. But this is P less than PC. So here, so the point is that, why is this fading away? Oh, well. It wasn't charged enough. Sorry about that. No, I was charging it this morning. I should have charged it all night.
You can use old-fashioned way. Or...
Yeah. No, I can. I know, but just give me. Let's take some time away. But anyway. No, I know what to do. Just 1 second. Settings. Yeah.
Technical difficulties, but YouTube will be uploaded after. Yeah.
OK, there we go. And then I want to make this bigger. Sorry. Go on with your questions. What were you saying, Leo? Where's this? Where is accessibility? Display. This is highly non-intuitive, but a good trick to know. There we go. OK. All right, there. No, I'll have to. OK, so now if you look over here, P less than PC, which is over here. So here's the data. No, where's the data? I forget. Which is the data and which is the calculation? I don't know. OK. Yeah, I need my glasses now. Right, yeah, so the dashed lines, right, thank you. The dashed lines are data where the red arrow is. And this is a calculation for various Fermi surfaces. So if you take the large Fermi surface, which is the default assumption, it's completely wrong. It stops working. If you take various electron pockets that are somehow seen at very low temperatures in a high magnetic field, when you have charge density wave order, and that doesn't work either. But if you take this picture with pockets, over here, you take these small pockets, then it seems to kind of work. So now the thing about this is they've got this arc that you see in photo emission, but they've also got a backside. So now here the idea is that when you're doing magnetotransport, the quasi-particle Z doesn't come in. It's irrelevant. You just have your quasi-particle moving in the magnetic field. And whether it's an electron or a dressed electron doesn't make any difference. It's just that all you need is the mass of it. So the scenario would be there is something in the back. There's a quasi-particle at the back. It just has a very small Z, and so can't be seen in photo emission. On the other hand, photo emission, you're ejecting a bare electron. So the quasi-particle residue does matter. Here, you're not ejecting anything out of the sample, so it doesn't matter. Somebody had it. Yeah?
Now there's a relaxation time along the Fermi surface.
Yeah.
That's a function's worth of physics, perhaps.
Yeah. So I think they just take some momentum-independent relaxation. I'm sure they played with all of that, but it's very clear. Now, this is not entirely convincing that E is the correct answer, but I think it's fairly convincing that A and C are wrong. They just don't work. Yeah. No, that would be spin density wave orders most likely at pi. So they assume there's antiferromagnetism. They take the Fermi surface for antiferromagnetism, and you get a data that looks kind of reasonable. The only trouble is there is no antiferromagnetism. You can detect it by neutron scattering, and it's not there. But it gives a model that seems to be OK. All right, so this is the big puzzle. Photo emission says one thing, magnetotransport seems to be saying something quite different. Okay, and this is only 3 years ago, so the field continues to evolve. All right, so then last year, there's this amazing experiment called the Yamaji effect. So I'd never heard of the Yamaji effect, but now I know a little bit about it. It's basically the same experiment where you tilt the magnetic field and you measure the magnetotransport. Now, what Yamaji noted way back in '89, and this was applied and very successfully to various quasi-2D organic materials, that there's a certain angle, which is now called the Yamaji angle, at which the area of this ellipse, this object here, which is kind of elliptical, is independent of kz. So there's essentially no dispersion from the Onsager rule. You know that the dispersion in this direction depends on the, on how the area changes. Okay, but there it's independent. So in fact, at a certain angle in which the particle is dispersionless in the kz direction, meaning you have a flat band. So the certain angle is a flat band along the z direction. And this happens, for just a small cosine deformation, warping of the orbit along the z direction. Now here it's also very important that looking at this particular material, this mercury compound, which is very special. It's just a single layer cuprates, and the layers are directly on top of each other. So it's a pure, simple tetragonal lattice. So it does have, alone among the cuprates, a cosine band in the z direction. So I'm sure, Brad was the one who told me about this experiment. He would have been delighted to see a Yamaji effect. But this material that he's looking at, unfortunately, is much more complicated in its dispersion in the z direction. Anyway, so the key is to getting the right material. So what you would expect, because it's dispersionless in the z direction, is a peak in the magnetoresistance, because this becomes flat at that angle, so there should be a peak in the magnetoresistance. And then the amazing thing is, from the position of the peak, you don't need to solve any complicated Boltzmann equation. From the position of the peak, meaning the angle at which you see the peak, and the value of this number, 2 pi over c, c is the layer spacing, which you know very, very accurately, you can deduce, this assumes a simple elliptical pocket, as you can see. You can deduce the area of the pocket. All right. So first of all, they do see, so there's the Yamaji peak over here. And then from that, this is their assumption of what the angle is. Here's their measurements. Here's the solution of the Boltzmann equation. All seems to work very beautifully with the assumption of 4 pockets. And they can then read off the size of the pocket is 1.3% of the Brillouin zone area. Okay. So now there's not only they have a pocket, they have a firm number of how big it is. All right. Yeah.
In principle, isn't this whole suite included in the earlier Ramshaw experiments? I thought they were.
Yeah. So, but like I just said, that's a complicated material where the c-axis dispersion is not so simple, and.
It's not as qualitatively picky.
Yeah, well, I don't, I think you should really ask, this is all developing. We're also trying to redo the calculation for that particular material and see why it doesn't happen. I think Brad said he's done it, redone this calculation for the LNSCO compound, and he doesn't expect a Ramaji peak there. So yeah, that's what he told me, that he's not surprised at all that he didn't see it, and they saw it. Yeah.
I'm trying to understand, is this an independent conformational pocket? Like, I'm trying to understand.
This is the first clear evidence of a pocket.
But the magnetic resistance, you're saying there you have to model it.
Yeah, it's not as, I think this is far more convincing. And furthermore, it gives you a size of the pocket without any calculation.
I see. Because if you didn't have a pocket, you wouldn't have this interpretation in terms of a peak.
Yeah, the Imaji, it's been, the idea has been confirmed thoroughly in many other simpler materials. And I think people in magnetoresistance knew all about it, people who do magnetotransport, and they've all been looking for years. Now it seems to have been seen. Yeah.
What material is this?
This is the mercury compound.
Oh, okay.
This one here, that's where they're measuring above TC. And you can see the magnetic fields are not small. What is it? Yeah, up to 90 Tesla here. No, that's the angle, sorry. Where's the field? Somewhere. Yeah, 72 minus 50 Tesla. There we go. That's large too, yeah. That is the key point of my talk, yes. So now we have a number. Can you explain this number? Okay, so what I'm excited about is that the spin liquid theory explains this number. All the other theories don't. So that's what I'm going to show you now. And we predicted this number in 2007. Yeah.
Also a mission on like many layer viscose,
Yeah.
where one sees pockets clearly, and I guess you could take that to mean either.
That one, that's at very low doping where there's antiferromagnetic order. So there, everything's fine. And the inner layers have antiferromagnetic order there, and that acts on the outer layers. And then you see very clean pockets, they are basically these pockets. You see them very nicely at very low doping in photo emission. You even see the backside. And the area there is a bit different, though. That works with the spin density wave theory. So this is the work of Kondo and others here. There's been several recent experiments on 5-layer, 6-layer visco. When you go to the pseudogap regime in those materials too, at higher doping, you just see the same thing. Yeah. Yeah. Well, I hope, yes. I'm sure, I think this is, I think these have to be clean samples. And the doping here is 0.1. And yeah, it would be great. But I think this paper has just been accepted for publication, and I imagine they're working on it.
Sorry.
Yeah.
Maybe I should just read the paper, but they don't have like so many data points. So obviously there's some sort of error bar on the size of the pockets. Is there some sort of order of magnitude that we can describe?
Well, so it's a question of the error bar is, all you need is the angle. So what's the error bar in determining the position of that peak? That's it. You need the angle, and you need the c-axis spacing, to 5 decimal places. That's all. You need the value of theta, and that's c, and that gives you the area. That's it. So you can judge for yourself. Okay. All right, so here's another old experiment. I don't know if I'll have time to come to our theory for this. So this is a picture, so what I said last time, whether the D-wave superconductor at low temperatures is basically the same at any doping. It's D-wave, there's no quasi-particles, and as you scan doping, which many people have done very carefully, you don't see any dramatic change in anything. However, there is one qualitative change, which is quite dramatic, which is the vortex. So you can look at the vortices in the magnetic field using scanning tunneling microscopy. And first of all, you confirm that every vortex has flux h/2e, as it would in BSS Landau-Ginzburg theory, everywhere. But if you look at the core of the vortex, these are the vortices, you see these modulations in the local density of states, which were discovered in this paper, 2002. And this you only see on the low doping side. You don't see these modulations on the high doping side. Okay, so that's qualitatively quite a significant difference in the superconducting state below TC. So, and the high doping side, there is something called the Wang-McDonald theory. This is Alan McDonald, which is essentially the usual de Gennes-Bogoliubov theory for D-wave superconductors. We just do that. It works very well on the overdoped side. It doesn't work at all on the low dope side. It's basically the de Gennes-Bogoliubov theory, just Landau-Ginzburg theory, or no, it's Bogoliubov-de Gennes theory in the presence of a vortex. So that has these de Gennes-Matricon modes for an S-wave superconductor. If you redo that for a D-wave superconductor, you actually get a big peak, which is gapless at low energy, which people call the Wang-McDonald peak. Yeah. But you don't see the Wang-McDonald peak in the underdoped, you see it in the overdoped. Yeah. Yeah, I don't think so, but I don't, I think people are studying some of that. It's not so easy to study that. Yeah, there's a group in Switzerland, Geneva, that's doing that. I think Seamus might be too. All right, so let me just quickly review some old theories. So the oldest theory, I would say, is some kind of phase fluctuation theory of Emery and Krivelson, where you start from a D-wave superconductor, which has nodal points, and then you just heat it up. So the way you model it is you take the Bogoliubov Hamiltonian, which has a pairing gap, and you assume the pairing gap locally is given by the autoparameter of a thermally fluctuating XY model. So you just write down an XY model. You do a Monte Carlo simulation of it at finite temperature, and you get some phases, some random phases at every point. You put those random phases in a Bogoliubov-de Gennes Hamiltonian. You find the eigenstates of all the fermions in that Hamiltonian numerically, and then you average over different random phase configurations. So that's a kind of calculation I'm going to do, but in a very different model. Anyway, so that does give you these Fermi arcs. So that's good. So people, that's fine. But once you get above here, if you go to high temperatures in this theory, then you just get back the full Fermi surface. So that's a problem.
C still very angular dependent.
Yeah, but you don't see any restoration of the antinodal Fermi surface in the experiment. Yeah.
Would you say the Yamaji effect observation that happened in the charge order part of the?
No, no. So one way you know is that the Hall coefficient is positive there, whereas once you have charge order, the Hall coefficient turns negative. Yeah, I had a long discussion with Louis Taillefer on just that point last week. Yeah.
So when you're saying that this gives you the Fermi arc, so did you mean that this is only for temperatures very close to TC?
Well, I mean, it depends on the model, but there are many, so here's a more recent reference. Many people have done this type of calculation and continue. Yeah. All right, I mean, it's a question of taste, but to me, it seems a bit implausible that this picture works well so far above TC. But this picture has absolutely no way of explaining the magnetotransport. There are no pockets in this thing. There's only arcs and the big Fermi surface. Okay. So another point of view is to come from the ordered antiferromagnet and look at its fluctuations. And I think Andre may have said something about this. So this is a spin density wave theory. And there, if you take a static spin density wave, which was what was done here. Over here, you get these 4 pockets, and then you put thermal fluctuations on it, and further quantum fluctuations on it, and there's been an enormous amount of very nice work done on that by André-Marie Tremblay and Andrei Chubukov and others. Yeah, so that kind of, it works. Actually, the way it works very well, in fact, is in the electron doped cuprates. So in the electron doped cuprates, this line here with antiferromagnetism disappears, comes all the way out to the middle of the dome. It's much bigger. So the antiferromagnetism is much stronger. And if you were just above, if you were above here in the electron doped cuprates, it works. And over here, too. That was the photo emission you were referring to. That's over here. Okay, for the whole dope cuprates. But so it can, and it can also give you, it'll give you pockets with some very reduced intensity at the back, and it can also give you pockets in magnetotransport. So that's good. But as we'll see, the area is wrong. Okay, so that's what I'm going to explain now. All right, so I'm going to talk about some relatively recent work, and in collaboration with many people. I should mention Maine Christos. She's just graduating. Otherwise, I hope she couldn't make it to this school, but she's going on to Caltech as a postdoc. There's a current postdoc, Pietro Bonetti, who's played a key role. And Alex Nikolenko is my current student. And various other people. Yashin is here somewhere, I think. Okay. And if I have time, I'm going to show you some recent Monte Carlo simulations of this gauge theory done in collaboration with these 3 people in Chennai in India. All right, so before I go into any fancy theory, I'm just going to try to explain the basic idea of the spin liquid theory of the pseudogap just by drawing cartoon pictures. And you might think, well, that's pointless. But the idea is that Fermi surface areas are very robust things. You can do a very, very crude theory, but as long as you have the right phase, you will get the right area of the Fermi surface, which is robust to all corrections. So we're going to focus on the Fermi surface area. So as I mentioned in my first lecture, there's the Luttinger theorem from 1960, which says that the area of the Fermi surface is that of free fermions with the same symmetry. Now, Oshikawa put this on a non-perturbative footing. Today, we'd say some kind of anomaly matching argument. There's an anomaly associated with global charge conservation and translation that you can compute exactly for any system. It's just basically the density of particles. And then knowing the value of the anomaly, you have to match it to your favorite theory of your phase of matter. So if you just have a Fermi surface and you compute the anomaly of that Fermi surface, you get the right value if and only if the area enclosed by the Fermi surface is the same as that of free electrons. So there you're done. However, there are other phases of matter that can have anomalies. And that's where you can get Fermi surfaces then that have different areas. And so the Fermi surface area, at least deviation from the Luttinger value, becomes an extremely sensitive test of entangled phases of matter. It can tell you it's there or not just by the area. So it's sort of like, but not as good, like the Hall conductors. If you get a certain fractional Hall conductor, you know you have an entangled state of matter. All right, so there are these things we call FL star, where the Fermi surface area is not equal to the Luttinger value. And so by the anomaly matching argument, there has to be something else that makes up that anomaly. And that something else is a spin liquid. And so we just need a spin liquid, which is exactly at half filling. In fact, that's what we're going to look at. We know it's an anomaly. It's just associated with 1 electron per unit cell. And so you can get a Fermi surface area which differs from the full area by 1, because 1 is subtracted away by the spin liquid. All right, so let me show you some pictures of the possible states. So of course, if you have an insulating antiferromagnet, then there is no Fermi surface. If you have free holes of density P at large doping, then you get an area of 1 plus P over 2. So these are areas in units where the area of the Brillouin zone is 1. So that's 1. So this means that when P is equal to 1, the whole Brillouin zone will be occupied. That's the empty state, and there will be no Fermi surface. So where does the density of holes is 1 plus P. This is density of holes 1 plus P because you're always looking at density relative to a filled band, not the half filling, okay? So in the Luttinger count, you count everything. Everything is mod 2, of course, which are filled bands. So the density, true density in the Luttinger count is 1 plus P. The factor of 2 is from spin. There's 2 states for momentum, so you're down by a factor of 2. And that's exactly what you see. All right. So now let's take an ordered antiferromagnet. So this is the kind of state that Andrei Chubukov and others have been talking about. So this has the pockets. And what is the area of each pocket? Here, by area, I mean something that would appear in the Yamaji effect or quantum oscillation. What would you see in some kind of magnetotransport experiment? So here I claim the answer is P over 4. And why is that? Well, first of all, you know from microscopic calculations, you could just take a simple free electrons moving in the background of the antiferromagnetic order, and you will get this answer. So you have antiferromagnetism. So let's be at 0 temperature first. And so you have doubled the unit cell. And the dashed line is your new unit cell. I should be charging my thing. All right. Sorry, not unit cell, the Brillouin zone. You double the unit cell, and the dashed line is the reduced Brillouin zone, the magnetic Brillouin zone. All right, so that means that there's really only 2 pockets here because the top half of this pocket is the same as this region here. So you only take 2 of them. So there's 2 valleys. There's not 4 valleys, there's 2 valleys. There's a factor of 2 of spin. 1 is taken away because now your Brillouin zone is doubled, and one site per unit cell, 1 electron per site is 2 electrons per unit cell. So you can forget about the 1. So you're putting P holes in 2 valleys with 2 spin. So you get P over 4. All right. And P over 4 is not 1.3%. P is 0.1, you can work it out.
Well, I don't know what the answer is, but if you dope an antiferromagnet with some finite density of holes,
Yeah.
if the state still breaks, is it still stable? The magnetic order is still stable?
Yeah, so, that's exactly what we want to. So I think there's a difference here between quantum and thermal fluctuations. If you imagine you have this and you heat it up, as you do, say, in the electron-doped cuprates, then you're going to get thermal fluctuations, and this autoparameter will fluctuate. And the Fermi surface will become sort of fuzzy. But I don't think the area will change. The area is a very quantum effect. Thermal fluctuation won't change the measured area of this thing. They may become a little fuzzy, but they're not going to.
No, but I'm even asking at 0 temperature.
Yeah, but.
Antiferromagnet with finite density of holes, is that a stable?
Well, it may not be. So then you have to do a proper theory of that state that you get where the antiferromagnetism disappears. That's exactly what my first 2 lectures are about, is how you do such a theory. Now, you could try to do the theory just in terms of fluctuating autoparameter. We know in half-filling that theory is completely wrong because it violates the Oshikawa, Hastings, Leib-Schultz-Mattis theory. So if you apply that here, well, I don't know. I think I would say that, so that theory for finite doping could work. That would be called the Hertz-Millis theory. That could work. And now the question is, does the Hertz-Millis theory and the disordered size have a gap. I have a pseudo gap. And, I think Andre's been studying that, and it's kind of,
You could sort of like, if the long-range orders are stable,
Yeah.
speaking, you don't have this,
well, I would say any theory in the Hertzsmillis framework that has tried to go from here to phase with no long-range order, it may work, but basically what it does is restore the large Fermi surface. It doesn't change the area of the pockets. Yeah.
Yeah, sorry, while you're interrupted, just going back, this Yamaji,
Yeah.
which I've also never heard of, its general property when you have pockets of Fermi surface, or it has to do with specific material?
For any Fermi surface, could be a Yamaji effect. The only requirement is be quasi two-dimensional. So the warping has to be very small. So the dispersion in the c-axis should be much smaller than dispersion in the plane. That's the only requirement.
But the peak has to do with the pocket size, or
The angle has to
the
do with
angle of the peak?
Yeah. So just look at this picture. From this picture, it seems implausible that this area doesn't change as you slide that thing up. So what happens is that you expand in the bandwidth in the z direction. Let's call it. So there's some t perp. This is a t perp. So the area is some function of t perp, and it turns out that the area becomes independent of independent of kz. To first order in t perp. There's still some variation, but it's second order in t perp.
decreasing one and increasing the other.
Yeah. I mean, looking at this picture, I would never have imagined it, but you do the calculation. It's just pure geometry, and you find that there's certain angles at which the area only changes to order t perp squared, whereas, that's the Yamaji angle.
And that fact has to do with pockets or arcs, or that's still general?
No. So even the large Fermi surface could show you Yamaji angle. I don't know if anybody's looked for it. I would think it does. Yeah.
So presumably, less doped samples of mercury
Yeah.
exist. There, does one see the PO4 in magnesium resistance?
I hope. I think it's not so easy to change the doping this particular material, but yeah, I have no doubt they will. I mean, photo emission sees PO4, no question. So in the photo emission, they see the full pocket, and the area they have is PO4. There are several papers with that value already. Yeah. Okay, so why is the spin liquid different? So now let's just do an honest, at least not so honest, but a cartoon calculation of the type Leo wanted. So let's disorder the antiferromagnetism. So what are the spins going to do? They're going to form singlet bonds, okay? So this is now a spin liquid state with some empty sites. So they can resonate. And the sites can move around. And as the sites move around, you see that you're carrying charge, but you're not carrying spin. Okay, so these vacancies have charge E, but spin 0. So in a spin liquid background. In an antiferromagnet, they actually do have spin 1/2 and charge E. But here they have charge E and spin 0. And depending on the theory, but in a large class of theories, including the certain quantum dimer models, these vacancies would be fermions. Okay, so these vacancies we call holons because they don't carry spin. And if they're fermions, then I can apply the usual Luttinger argument to the holons. Okay, that's because it doesn't care about electrons or anything. All it requires is a global U1 symmetry, and the density of these holons is fixed. So what does the Luttinger argument, these holons, tell us? Well, the Luttinger argument to the holons will tell us that the total area should be P, because that's the density of the holons. And in most people's calculations, you get 4 pockets. But these are spinless. So now you have 4 valleys, but 0 spin. So you get P/4 again. But for very different reasons. Okay, so the hole-on metal state, where you have free charge E particles moving around, would give you this. Now, there's other problems with this state, because in photo emission, you would see nothing, because you can't eject this hole-on from the, if you do photo emission, you will eject a hole-on and a spin-on, because an electron has both spin and charge. So you'd have to break one of the singular bonds that's going to cost you energy, and so you would not even see the Fermi arc. So this is not a reasonable state in anybody's point of view, but it could be responsible for magnetotransport. But it just gives you area P04. You may or may not, depends on the dispersion and so on. So there's various calculations you can do. And the simplest one are these things where you go to a rotating reference frame of the antiferromagnet and you disorder it with Schwinger bosons, you get the 4 pockets. Yeah. There was a period in my life where I thought this was the theory, but okay. Fortunately, I gave it up before the Yamaji measurement.
Before you go, is spin liquid has to be some Dirac nodal?
It could be any spin. So first of all, yeah. So this is some quantum dimer, very trivial RVB state. But again, the point is, it doesn't matter what spin liquid you have, as long as it's some spin liquid at half filling, and it has charge E fermions as its lowest lying quasiparticle, then the area has to be P04. Or total area has to be P. You may not get 4 different pockets, but
Yeah, just wondering if the pocket some kind of a consequence of nodal.
no, the pockets are. I mean, it's a consequence of short-range antiferromagnetic order. For the same reason in the antiferromagnet you get those 4 points, for a similar reason. But they're not exactly at the Brillouin zone boundary. In fact, there is no Brillouin zone boundary. Yeah, so they can move. There's no magnetic boundary, so that's why I haven't drawn it. And they can move around. They can be different places. All right. So what's going to save the day? Well, so what can happen, and there's lots of calculation now showing that is what happens, is that now this spin liquid also has spin-ons in addition to the hole-ons. So I have particles that can move around but carry no charge. But to create them, you go to an excited state. It costs you some energy to create them. They're not in the ground state. But the spin-ons can gain some energy by going near a hole-on and forming a bound state. So if the binding energy of the spin-on and hole-on exceeds the energy to create a spin-on, the spin-on will spontaneously appear out of the vacuum and lower the energy of the whole system. And now you'll have a new system, which we call FL star, where you still have the spin liquid, but the charged excitations are these bound states. So what is the bound state? These are these green objects. It's a bound state of a spin-on and a hole-on. And these can move around too. And in everybody's spin liquid, the bound state of a spin-on and a hole-on is basically an electron. It has to be a fermion. So these green objects are some highly renormalized, it has to be fermions. And the green objects are highly renormalized electrons or holes. They carry charge plus E, spin a half. They're not hole-ons, they're holes. And they can move around. And they're also fermions. So this is the state we call FL star in a very cartoon point of view. It's a spin liquid. So if you looked at this wave function, this very simple wave function in a colorblind way, it's RVB state. It's just some of the valence bonds are actually fermions and carry spin a half. That's all. And again, now you can apply the Luttinger theorem to the fermions, okay? So now what will be the area enclosed by the fermions of the Fermi surface? They have to form a Fermi surface. And what's the area? Well, so again, depending on there's various microscopic calculations. There's in fact also a calculation of precisely this model by Matthias Punk. And you get 4 pockets again. But now you have 4 valleys, and you have a spin degeneracy. So in a spin liquid, if you get electron-like pockets, the area must be P/8. Okay. All right. Yeah.
It seems like it's important to emphasize, if what I'm saying is correct, but correct me if I'm wrong. There's a distinction between this binding is just you creating a bound state between a spin and a holon,
Yeah.
like a two-particle bound state.
Yeah.
While this is to be just, and that's how you get FL star in violation of.
That is one way of getting FL star. I mean,
There's a confinement by the gauge field, which will return you back to the original non-fractionalized Fermi liquid.
Yeah.
Where there the
No.
Fermi
No. But this is not this is not the Fermi liquid. It's
No.
yeah.
I'm saying this one is FL star, but if instead you had a confinement transition.
Yeah.
The gauge field.
Yeah. So that's.
Return to the Fermi liquid originally.
Yeah, so that's a much more difficult transition to describe. I don't know how to describe it in these pictures. That's really, and in fact, that's the topic of my lecture tomorrow. But for now, yeah, I've given you a way to, how we came upon this type of state. But the trouble with this picture is that it doesn't let you really calculate anything. You can, you can wave your hands and say, yes, so they're hold-on, they spin on, they form a bound state. Okay, maybe you can solve some Bethe-Salpeter each equation and see the bound state formation. But then you have to take the bound states and take a finite density of them and form a Fermi surface. Nobody knows how to do such a calculation. So it's a correct picture, but it's not something that leads to any calculational method. And the remaining time, I will introduce a calculation method. Yeah.
So I'm kind of confused. Is holon is a fermion, right?
It depends on the theory. Some theories have bosonic holons. In fact, the earliest theories of ITC from Kotliar and Liu and others had bosonic holons.
But when you say bound state, spin-on is a fermion and holon is a boson?
So it goes the other. So in some theories, the holon's a boson and the spin-on's a fermion. In other theories, the holon's a fermion and the spin-on's a boson. We saw those theories. And then in both cases, the bound state is a fermion.
Okay, yeah.
So this green is always a fermion. It doesn't matter whose theory. Yeah.
Could you maybe reiterate what's the difference between these kind of like dress fermions and just having the spin-ons and the holons confining it in some way?
Well, because you're only confining the holons of the spin-ons. The spin-ons are still there. This state still has free spin-ons. It still is an RVB state, and you can still break these bonds and have a free spin-on moving around. It's still a fractionalized state.
So just like some of the spin-ons are confining to the small amount of holons, and you have a lot of.
All of the holons are taking a spin-on, no more. But there's still spin-ons left. The valence bonds are still there.
I mean, that's a distinction I was trying to make.
Yeah.
Phase of that gauge theory or deconfined state of that gauge theory, but with a two-particle bound state, not like
Yeah.
gauge field, but like just a bounding potential.
Yeah, in fact, you can see very easily this bound state always wants to form because the energy cost to create a spin-on is J, of order J. The energy gain by forming a bound state is T, because this thing will hop back and forth with amplitude T. So you gain energy when you do that. So at any model with T bigger than J, this will happen. And there's a lot of numerical evidence supporting that. Yeah.
Yeah, so why the area is P over A?
Well, therefore, the total area has to be P over 2. So depending on the model calculation, it could be 4 pockets. And I will show you, I mean, there is a model calculation that has 4 pockets, this paper here. This is a numerical diagonalization of this quantum dimer model. And so you have 4 pockets, and you have spin degeneracy. So unlike the holons, we didn't have the spin degeneracy. So it's 8, so P over 8. So to summarize, I think I have a slide here. Yeah, here's the summary slide. There are 2 different areas, but all for different reasons. In the antiferromagnetic metal, you have 2 pockets because the Brillouin zone is halved, and you have spin degeneracy, so it's P over 4. Here you have 4 pockets, but no spin degeneracy, so it's again P over 4. Here you have 4 pockets and spin degeneracy, so the area is P over 8. Yeah.
But if you want P over 8,
Yeah.
you want to saturate the mu equals 1 anomaly using some state which doesn't break translation.
Right, exactly. Absolutely. And you need a spin liquid with, like a quantum dimer model is anything that has, you can see in this picture, like roughly speaking, there's one valence bond per site. No site doesn't have something going on. So the spin liquid, and that's the important thing that many of the earlier theories didn't properly account for. The important thing is that there's a certain rigidity to the spin liquid. Even when you dope it, there's certain things in the spin liquid that can't change, one of which is the anomaly. Yeah.
So in the picture that you drew yesterday for the RVP state,
Yeah.
this one, it seemed important that there was a spin gap, so that I can define the spin-ons as nicely.
Yeah, sure. So right. So that's a problem with this particular model that I'm sketching here. That's why it's a cartoon. Yeah, this gives you a large spin gap, and at least, I mean, these Fermis, there are some gapless spin excitations here, which are fermionic. So it's not true spin gap. But if you break these bonds, there's a gap. But now I want a method that can apply to more reasonable spin liquid rather than this simple dimer spin liquid.
So you want to know a couple.
And that's the purpose of the rest of my talk, but yes.
Okay.
No, go ahead.
You want a couple now?
But that is exactly the problem I've been struggling with for decades, actually, I would say. How do you take this? Well, since we wrote this picture, not quite decades. And yeah, that was 2015, 10 years, yeah, a decade. Okay, this is nice, but what about something better? And this ancilla method that Yaohui Zhang came up with is the trick.
What is the 1.3%?
Okay, before I get there, so this is just to show you, we actually predicted this. Here's a paper in 2007. We said this area is delta, which is P over 4. This is P over 8, okay. All right, so yes, this is the thing I showed you. All right, P over 8 is 1.25%. Okay, not exactly 1.5, but pretty close for P equals 0.1. Whereas in the spin density wave theory, you get 2.5, and that's clearly not what they see. They see something much smaller. And yeah, so I don't know if this is conclusive, but it's certainly the best evidence for fractionalization yet. That doesn't mean it's good evidence, it's just the best. Being very careful. 0.1. Yeah, let's say that there. So there's obviously some error in that 0.1, but it's not a factor of 2 error. It's not 0.2, which you would need, or 0.05. It's definitely not 0.05, which you'd need to get. No, you need 0.2 to satisfy the SDW criteria. It's definitely far from that. Okay, great. So you can see why this is giving a real boost anyway to thinking about the cuprates as spin liquid. They did the pseudo gap in the spin liquid. All right, so now I want to answer the question that Akshat raised. Can you do this for a more realistic spin liquid? Can you describe the Eiffel star in a more realistic spin liquid? And do it in a way in which you get the Eiffel star state already in a mean field theory. Then you can start doing all kinds of stuff. Right now, I'm showing you Eiffel star after some lengthy calculation that no one knows how to do. But we can still make some statements about it. Yeah.
Is there data like around optimal doping? Do we know if this is a crossover to the overdose normal metal or phase transition?
Okay, so if I go back to the phase diagram, this is what I will be discussing a bit tomorrow. So, so if I take FL star and FL and I continue them down to 0 temperature, then there is a quantum phase transition between them. And a lot of effort has been expended in trying to figure out some complicated gauge theory, and which nobody really knows what happens to it. Okay, but what happens is that, in fact, the spin liquid we're going to work with is unstable, and it's unstable to superconductivity. I showed that last time. So if you get superconducting, then in fact, there is no phase transition because it had no autoparameter. So this is kind of different from, say, you have antiferromagnetism, and near the antiferromagnetic critical point, there's a superconducting dome. Then, once the superconducting dome appears, there's still a critical point. Maybe I should be drawing this. So, yeah, this is an important point. So, I maybe raise this one. Correct, yeah. So, I don't know. So, if you had something like this, oh, that's still visible. So, this is, say, antiferromagnetism. And there's your superconductor. And for the hole doped electron doped cuprates or the pnictides, this may well be what's going on. You get phase transition even inside the superconductor. But if you have, and this will be the topic of my next talk, temperature doping, the cuprates, there's a zero temperature quantum phase transition between FL star and FL, which is only at zero temperature. And once it becomes superconducting, then there's nothing. It just disappears, which is also a good thing because nobody's ever seen anything like a critical point inside the dome. You could apply a magnetic field to get rid of the dome, but then you do get broken symmetries of other kinds. I've been hoping that you could finally see the naked FL star FL transition in a high field, but yeah, that hasn't happened. There's always something else that happens. Yeah.
One also needs a phase transition between the very lightly doped antiferromagnetic metal and an FL star. Right?
Yeah. So absolutely. That's a relatively easy transition. You just condense bosonic spin-ons. Yeah, we have a paper on that. Several papers. I think also Central has papers on that. All right, so let me at least give you the introduction to the actual method. So what we're going to do is reduce this thing to a problem already solved. And a problem that's already been solved is the Kondo lattice. On Kondo lattice, it's actually quite easy to get an FL star. So I imagine this is not, I'm not describing the cuprates yet, but I imagine I have some one layer of square lattice, say, of spins, and another layer of conduction electrons in a different band of density P, okay? So then there are two possible phases the system can form. What people call the heavy Fermi liquid large Fermi surface phase, which is seen in literally hundreds of materials, heavy fermion compounds with heavy electron masses of 100 or bigger, is this phase on the right. It's a conventional Fermi liquid phase where you count the spins in the volume of the Fermi surface. And there's a theory for it, which I'll show in the next slide. But what can happen if, under the right conditions, and it seems like in cerium, cobalt, indium-5, that does happen in some recent experiment by Jim Analytis and others, is that the F electrons can form their own spin liquid. And then this Kondo exchange is not a relevant perturbation. It doesn't always flow to infinity. And the C electrons will form a small Fermi surface of size P. And that would be FL star because you're violating the Luttinger theorem. But you're OK with the Yoshikawa theorem because you have a spin liquid hanging around. OK. So how do you describe this? Well, it's very simple. Well, simple now, but it's something that's been worked on for 30 plus years and is really quite successful in this context. You write the spin in terms of some spin-ons, which I call F1, for reasons that become clear in a minute. And then you put this ansatz in here, and then you just factorize that, do a mean field theory of that. It's just do Hartree-Fock theory for F's and C's, F1s and C's. So the simplest ansatz, in this case, I'm not going to do the SU2 stuff. The simplest ansatz is just that this leads to this hopping term between the two bands. People call it the hybridization. There's a hybridization phi, and the value of phi is determined by some kind of self-consistent calculations. on the original Hartree-Fock theory with this Hamiltonian. So in the early days, this was just done for these two terms. You didn't put the exchange interaction between the S1 spins. But if you put those in, what you find then that there are actually two possible solutions. One is phi non-zero, and the other is phi equals 0. So when phi equals 0, the spin liquid and the conduction electrons decouple from each other. And so that's the basic picture, okay? So you've got two phases, one where phi is condensed, the other way it's not. And the Fermi surface volume in the mean field theory doesn't quite jump. It has some very complicated reconstruction right near the boundary, and you also have to include a gauge field for the fluctuations, but you know how to do that from yesterday, or day before yesterday. So, and this has been studied a fair amount, and I will say more about it tomorrow. Okay. So that's it for the Kondo lattice. It's really very simple. You get an FL star state simply by setting phi to 0 and decoupling a conduction electron from the spins. The trouble with the cuprates is that I don't know which is the conduction electron and which is the spin. I can't simply just decouple it. Yeah.
So does the surface size?
Well, it goes through some very complicated shapes as you go through. Well, so to get this transition to work, you need to take a spin-on Fermi surface. So on this side, there's the C electron Fermi surface, and then there's a spin-on Fermi surface. And they just hybridize with each other in some complicated way until eventually you only have one band that's filled. Yeah. What is true that so in the main field theory, phi becomes non-zero continuously. So it's a continuous transition. And the quasi-particle residue on this Fermi surface vanishes here and then reappears on the big Fermi surface. Yeah.
So in a lot of heavy Fermi systems, you still have an FL phase, in which case they don't form a spin liquid, they just form electromagnetic order.
Yes. So that's why I don't have the reference. So there was a paper written by Senthil, Vojta, and myself, 2004 maybe, where we pointed out, despite the experimental evidence, that there should be this other phase that's possible. And now there's several compounds where there's signs of it. Yeah. And I think this is the actual transition underlying what you call Kondo breakdown. But okay.
But in the Kondo lattice, is there still a electromagnetic phase?
There could be, yeah, of course, that's possible. So the phase that everybody had, the phase diagram that everybody drew before our paper, as you just mentioned, this was replaced by antiferromagnetic order. And we said, wait a minute, there's another more interesting possibility. There can be a phase transition without any autoparameter, and you could get the spin liquid type phase. Okay, so we predicted this phase. Yeah.
So is there any way in this picture to choose a parameter and get to the case where actually the spin-ons and the holons would prefer not to bind? Or would that
No, but that picture doesn't apply here. It's very simple. I'm not binding anything. I already have the C electrons to begin with. This is just Hartree-Fock theory. It's very simple. It's orders of magnitude simple than what I talked about for the one-band model. It's just, all I did is, all you have to do is make the substitution in here and then to Hartree-Fock to get this. And then you also have to play with this J1. You also have to Hartree-Fock that one, sorry. And this is what nobody did before our paper. I'm sorry, the reference is not here, but anyway. And so, depending on what this J1 looks like and RKKY coupling and so on, you could get antiferromagnetic order. But we're saying under the right condition, if the J1 is sufficiently frustrating, maybe you get a spin liquid with the wrong size Fermi surface.
But generally, you get three phases, interferromagnetic and then two of these.
Yeah, there could even be antiferromagnetic star, and yeah. So that's ongoing topic of research. It's a very complicated phase diagram. Chi Miao C also has, and Pierce Coleman.
So you say this is very similar to what? I mean, really, because of the constraint,
Yeah.
really still, with fluctuations, really like gauge theory.
In the end, yeah. but what we learned from this is, if you're going to make progress in anything in physics, reduce it to Hartree-Fock. And that's what I'm going to do for the cuprates now. But of exotic particles. All right, so here's the idea. Now let's apply the same Kondo lattice idea in the last 10 minutes to the cuprate. So you have a one-band model, okay? So I'm just looking at it edge on here. And let's see, maybe this thing is working now. Okay, that's working. All right, so you have a one-band model that I'm looking edge on. And I want to get an FL star phase. So at this point, I'm quite desperate. I'm willing to do anything. I just want some model which correctly accounts. It's like the foolproof. It's the dummy's guide to Ishikawa's anomaly. That even a dummy would obey Ishikawa's anomaly. I just do Hartree-Fock, and I will get an FL star phase. That's all I'm asking for. Okay, all right. So the key thing here is to do kind of an inverse RG. We're going to integrate things in rather than integrate them out. So I'm just going to take some ancilla system, which is at the moment totally decoupled. This is the system I want to describe. Just for fun, I have a bilayer antiferromagnet with this coupling J perp, which is quite large. And so these spins, S1 and S2, will just form singlets. So it's like a trivial gapped insulator, okay? And in fact, if you think that integrating in is something you've never done before, you're wrong. That is effectively what Hubbard-Stratanovich is. I'm just doing Hubbard-Stratanovich in a Hamiltonian formalism rather than a path integral formalism. And so this object, for example, this is the ground state. It has a spin 1 excitation, the triplon, where the singlet can break into a triplet, and the triplet can hop along. So that's the paramagnon. And if you have a Hubbard interaction in your model, and that's what Hertz starts his theory with. He takes the Hubbard interaction and decouples it by Hubbard-Stratanovich transformation, introducing a spin 1 particle. That's all I'm doing here, but in a slightly different way. All right, so now it's actually easier to think the other way. So this Hamiltonian with decoupled Hubbard model on the top and bilayer antiferromagnet on the bottom, before I get to that, so you might say, I can add anything. Why don't I add some other model? All right, it's very, very important if you want to satisfy the Yoshikawa anomaly that you add something that has a gap, and the ground state is a simple product ground state or smoothly connected to it. If you don't, you'll run into trouble. And there's infinite number of papers in the literature that have run into that trouble. You have to make sure that you always add something trivial. All right, so now this is the basic result. This model down here is exactly equivalent to this model. So what's the model down here? The model down here is just free electrons. So that's the difference from here. It's free electrons. But now these free electrons are not decoupled from the other system. They're coupled by a coupling antiferromagnetic JK coupling. That's the leading effect. Okay. All right. So now I claim that if J perp is very large, I can do an expansion in 1 over J perp and do a unitary transformation and connect all states here to all states there. These are the same Hamiltonian, just in a different basis. Okay. So that's a Schrieffer-Wolff transformation. And, and it's kind of easy to see why. Because, imagine in this system there's an electron here. So it's occupied. Well, if the electron is here, it's coupled by JK to these spins. And so from that coupling, it's going to lower its energy. So every time a site has spin a half, it lowers its energy. Now, if that site has doubly occupied or empty, it doesn't lower its energy because it's not coupled to the. So that's effectively what U is. U is something that lowers the energy of the half-field sites. The other part is the chemical potential, which also get renormalized a little bit. Anyway, so at least at large JPerp, I can rigorously work with this model rather than that model. And this is a 3-layer system where I have this Kondo coupling, but the Kondo coupling between the conduction electron, not just one antiferromagnet, but 2 of them. And I have to have 2 because if I just had 1, the 1 does not have a trivial ground state. There's no way I can write down a ground state with a broken symmetry for a single antiferromagnet at half filling. That's essentially the statement of the Lieb-Schultz-Mattis Oshikawa-Hastings theorem. Okay, so now let's just go ahead and look at this model. So this is only justified at large JPerp. And at large JPerp, life is kind of boring. If JPerp is really large, these spins will form a singlet. That will form a Fermi surface. The size of the Fermi surface is 1 plus p. I'll be back to where I started. So the only way something exciting can happen is if JK becomes larger than JPerp. Now, why would that happen? Why would it be a reasonable thing to do? Well, we know from the single ion Kondo effects, so just pick one spin S1, which is coupled to this conduction band. That's a Kondo problem. And we know the RG in the Kondo problem is J Kondo goes to infinity. So let's imagine we do some RG, wave our hands a little bit, and JK becomes large. So let's just ask, what is the ground state when JK becomes large? Well, it's precisely FL star. Because what happened? So when JK becomes large, the top 2 layers is just a Kondo lattice. I just told you what a Kondo lattice does, 99% of the time. Well, 98 maybe. It forms a big Fermi surface where you count both the spins and the electrons. So it's kind of a trivial phase of the Kondo lattice, which is the FL phase, which is seen in essentially all heavy fermion compounds. What is the size of the Fermi surface here? Well, let's just count all the electrons here. I'm counting holes. 1 plus p on the top, 1 in the middle. That's 2 plus p. Everything is modulo p, 2, sorry. So the size is p. So the top 2 layers, bingo, give you total density p of spin-a-half chargey quasiparticles forming a Fermi surface. So done. That's what you wanted. However, so this is the trivial state for the Kondo lattice. It is not the trivial state for the Hubbard model, single-band Hubbard model. There, the Oshikawa theorem tells you there has to be a spin liquid around. And where is it? Well, there it is, at the bottom. You can't forget the bottom layer. It's there. And so this thing is only stable if the bottom layer forms a spin liquid. And there it is. So now you have the very simple mean field theory of this 3-layer Kondo lattice model, which gives you an FL star phase. Okay. That was here, right?
So this RG argument, usually JK goes to infinity if there isn't any other thing competing with it. Here you have JPerp competing with it.
Yeah, sure, right. So
you have to tune JK to be larger than JPerp in some sense, and then.
Right. So, like I said, I don't know how to make this quantitative in the interesting experimental regime. It just gives me the right phase in mean field theory. So now I can start to study its properties in kind of a semi-phenomenological way. So for some mysterious reason that I have not explained, perhaps the Hubbard model, single-band Hubbard model, is smoothly connected to this phase of the 3-layer model. That's all I'm assuming.
But the case where JK is 0, right? That's where you.
Yeah, then you will only get a Fermi liquid.
That's not smoothly connected because that's on the right side of this transition.
Yeah, so there's a phase transition. So this particular model, the 3-layer model, I can show quite reliably has a quantum phase transition as a function of JK between 2 different phases with different size Fermi surfaces. Okay. And now I'm hypothesizing without proof, but maybe you can know. So there is work on for example, you could take this wave, you get a wave function from this, you can compare that to cold atom experiments. So there's a couple of papers doing that. One by Henry Shackleton, and it works quite well. You can compare that to various numerical and experimental observes in the Hubbard model. That's the only way I would know how to really make this work. so far. Maybe there's other ways. We'd love to see that. But now the hypothesis is that this side of the phase transition of this three-layer model maps onto the underdoped side of the Hubbard model. That's a reasonable hypothesis that it's smoothly connected. I think that's quite reasonable, given that I'm preserving all the anomalies in the canonical transformation I showed you last time. I mean, you can extend that to any order you want. It's only, you could do the canonical transformation numerically. I just don't know how to do it analytically. If I want to do it analytically, then I have to do this expansion. But numerically, you could try to do it. Yeah.
So assuming the mapping to the three-layer model is correct, the transition between the two phases, is that just part-on-mean field theory, or do you see it in numerics?
Well, numerics, there are some DMFT calculations that show such things, yes, of FL star to FL, yeah. But yeah, they have to be multi-site DMFT. No, on the Hubbard model. There's no point doing numerics on the three-layer model. That's so much harder than a single-layer model. So you're going to do high-powered numerics work with the single model. I mean, maybe, okay, let's see. I mean, Yahoo's and others have been doing some numerics on this model, and it may be that you're able to access the phases of the original model more easily here. Yeah, it's possible. So maybe there's a point, yeah.
So I just want to understand a bit better the relationship between these two models that you presented.
Yes.
The FL and FL star,
yeah,
the same phases, basically in the two models. They're just two different ways to get a mean field theory for.
Yeah. So yeah, maybe that's actually a good way to put it. So I showed you these pictures of resonating dimers. I got a certain phase in a one-band model. I can now show that that phase in the one-band model is essentially smooth, has all the same properties as this one. I mean, everything is the same. Except here, I can get it in some controlled way in an unphysical parameter regime.
Okay.
Yeah.
So again, the spin liquid you want is not a gap spin liquid.
Yeah, so that's why I said now here, that's the power of this approach. You can put any spin liquid you want here.
But you have to show still that your strongly coupled form of field theory that lives on the last layer.
Yeah.
Its coupling to the metal with small Fermi surface is irrelevant.
That is the rest of my talk, but I'm out of time. That is exactly what our paper from last week is about. Let me just, so here's the full Hamiltonian, all the layers. And yeah, let me just show you very quickly in 5 minutes. So if we just decouple, so we take the Kondo lattice on the top and the spin liquid on the bottom. And in fact, here it's important that we take the pi flux spin liquid. If you take other spin liquid, this won't work. So if you so for now, you can take some spin liquid because B is the coupling between the two layers. That is the B I talked about last time. So here what happens is, this is it. No. Yeah. So here's your Kondo lattice. Here's your spin liquid, right there. And then you have a J perp. You Hubbard Sharanovich the J perp. And then you get this coupling, and this is precisely the B I talked about last time, in a very different way, from a single band model. It has the same quantum numbers and the same symmetry properties. So there's another Higgs boson. You set that equal to 0, means you have decoupled, and then you get these pockets of size p/8. But they have a backside. All right, so now what we've done more recently, you also can get this dispersion right. What we have done is in a quantum Monte Carlo simulation analogous to the phase fluctuation, but now it's a phase fluctuation of the SU2 gauge theory. And so when you do the phase fluctuation of the SU2 gauge theory, the main effect of that is to get rid of the backside. You get your arcs there. So I think I'll stop there. So this is really, and okay, one more thing. And at the same time, in the same calculation that gives you the arcs, you can still see that quantum calculation. Anyway, so this is our proposed resolution of the puzzle I proposed at the beginning. How do you reconcile photo emission and magnetotransport? Well, reconcile them by taking, this is the one thing you want to remember from this lecture. It's this slogan here. Where did it go? There. The pseudogap is a Kondo lattice heavy fermionic and a spin liquid. And when you couple them together and do some theory of the coupling, things work out. And also many other things in the superconducting phase, but all right. But I do want to talk about that because I mentioned this puzzle of VF not equal to V delta. Yeah, I'll talk about that next time. Yeah. Yeah.
So I just wanted to ask, so in the condo lattice, the original color you worked with,
Yeah.
when the two Fermi, F and C fermions hybridize, you're getting large Fermi surface.
Correct.
Here, when they hybridize, you're getting the small Fermi surface.
Exactly.
Dilated Fermi surface.
Yeah, so it's
That's because it's adding extra one.
So it's an inverted condo lattice. Yeah, so that has some experimental consequences. So if you look at various properties that are sensitive to particle hole symmetry, like power, you would predict an inversion between, say, a condo lattice system like cerium cobalt indium 5 as opposed to the cuprate. You would say that near the Fermi surface change, the thermal power should flip. And that's prediction in a recent paper with Avishkar Patel and Peter Luntz, and there's some circumstance, there's some evidence for that, but yeah. So that is definitely one of the predictions here.
Okay.
At the very beginning, you mentioned this Emery model. Is there any way to connect the three-band Emery model to the three layers here?
Curiously, I got an email from somebody yesterday on exactly that question. Wasn't you, though. Yeah, well, yeah, so there's a three-band Emery model, and here's a three-band model. But I don't think it's reasonable to say that, you know, I have a spin liquid that's sitting on the square lattice. It's really important that the spin liquid is on the square lattice, copper sites. Yeah, it's not on the ox. So I think, like I said at the beginning of this lecture, partly for the same reason, that there's zero evidence for a second Fermi surface or a second band, even away from the Fermi surface in the cuprates. All the photo emissions show only one Fermi surface, one band, excuse me. So you could start from the three-band model and project it to the one-band model. And that could give you further neighbor couplings of various types and some complicated hopping terms and so on. Fine. So these ancillas are just fictitious things. I think the way Yahui, I think he puts it in a very nice way. So, you know, what's complicated about the pseudogap, it has two different features. It has the feature of a Fermi surface, which is usually quite trivial, and it has a spin liquid. So how are you going to write down even a wave function for such a state? Well, the way you do it is you write down a wave function for the Fermi surface, which is here. Then you take some ancillas and you form a spin liquid. And then by this J-perp, you teleport the entanglement of the spin liquid into the physical electrons. That's what it's good for. And if you can use this to actually write down a wave function for the single band Hubbard model, that's what Henry worked with, and also Yasir Iqbal. And okay, that's kind of hard to work with. It has a sign problem, but it seems to be, at least for some correlators, work quite well with cold atom experiments. Yeah. Yeah, go ahead.
What is the intuition for the backside of the Fermi surface pocket during the photo emission? I.e., why is the residue zero?
It's not exactly zero. I mean, it's just, so this is a numerical calculation. Yeah, so I was very quick on that. So this is what we're doing. So yeah, so we're doing kind of a Born-Oppenheimer approximation. So here's the full theory. There's the Higgs boson B, and I gave you this E2 last time, and the SU2 gauge field U. And then there's the fermions in the three layers, the C, the F1, and the F. And the B couples the bottom layer to the condo lattice, couples the spin liquid to condo lattice. So what we say is, well, we're going to do the Born-Oppenheimer approximation, which is exactly what people in the phase fluctuation theory also did, except our fluctuations are of a fractionalized boson, not the paired Cooper pairs. So we're going to take a classical thermal theory of B and U and just simulate it on the computer. And for each value of B and U, we're going to completely diagonalize this Hamiltonian. So that's what we did. Okay. And then you keep taking more and more samples and diagonalizing and getting the data I just showed you. So this is how you get this. This is the data from that simulation. You take samples from this partition function of the Higgs field and the SU2 gauge field. And then what happens is the reason the backside disappears and not the front side, because the spin-ons are here. The spin-ons mix with the backside and get rid of it. So you actually, again, you really didn't need the spin-ons there. Only then you get rid of the backside. Yeah. Yeah, go ahead.
So following up on this, I guess, for the thermal fluctuations, what people did back then, you had critical slowdown, and it's, I guess, you have a reason to take Born-Oppenheimer approximation and assume slow dynamics. What's the reason to assume B has slow dynamics here?
Well, certainly near the costless-Thouless transition, it does, because the order parameters, both the charge order and the superconducting order, are just composites of B. So B, you can think of B as a fractionalized order parameter. It's like a bosonic thing whose product of two B's gives you the Cooper pair, and different product of two B's gives you the charge density wave, and so on. Yeah, that's all covered in the notes. Yeah, so but it's an assumption. I mean, you would like to put some dynamics for the B here, but then you have a sign problem. So.
For OIT?
Sorry?
Did you call OIT? Yeah, let's let him finish. Gotcha, sorry.
Yeah.
Thanks.
Yeah, so we haven't done it, but it's like I just said, the spin liquid we take has Dirac spin-ons right near the backsides. And that's really crucial to get rid of the backside. So for the fermion spectrum, it will change. I mean, the form of the Higgs potential, the fact that this Higgs potential gives you a D-wave superconductor is very special to the spin liquid. So many things work out that we haven't bothered to try anything else. Yeah.
So to get rid of the backside, it's some incoherent.
Yeah. Right.
So,
and we were only solving it in some approximation. Yeah. But it's definitely a thermal effect. We're saying it's a thermal. Yeah. Now, we would say that if you were able to stabilize the FL star down to 0 temperature, you would see the backside. And I was hoping yeah, but no one's ever been able to do that. Yeah.
in any one.
Partly the reason may well be because the spin liquid they're working with is actually unstable. So it's not supposed to be. If this was a Z2 spin liquid and you had an FL star, I think there's a much better chance you could stabilize that down to 0 temperature.
I mean, like being devil's advocate, when you were talking about the XY model with the strong fluctuations and doing this thing.
Yeah.
There you said, well, it's hard to imagine that it works at such high temperature.
No, but
here there must be something scale.
No, here the point is, not so much. So the gap here is very, very stable. Now, we have the gap for free. We don't need thermal fluctuations to get a gap here. So they need these superconducting order parameter disappear. Since they work with the large Fermi surface, you just get the large Fermi surface. Here there is, even without fluctuations, we have a gap. So the pseudo gap is determined by phi, whereas the pairing gap is determined by b squared. So the appearance of the pseudo gap here is a quantum effect. The disappearance of the backside is a classical effect.
Well,
The phase fluctuation theory is everything classical. Yeah. Yeah.
So two questions. First is, I guess, related to what you were saying. Do people see any temperature dependence then of the pseudo gap? Because here there's like a factor.
Yeah, well, we're not. So it's like I just said, it's the value of this phi that in the Kondo lattice that determines the value of the pseudo gap. So this is the part I skipped, I guess. Yeah, here. So if you take this just the b equals 0 model and try to map this pseudo gap with this, so here we get exactly the right dispersion, and so the value of phi determines this. So we're just fitting it to the photo emission. That's all. We just fit it to this data. You have to do a much more serious microscopic calculation to figure out its doping temperature dependence. We're not even trying to do that. Sure. So in fact, all these parameters, all the parameters on the top we fit to photo emission. Yeah, this J is, we don't know what the spin-on velocity is. And yeah, everything in here is just a free parameter. Yeah, go on, sorry.
Okay, so an unrelated question. Does this apply in any way to the electron lobe grouplets?
There may be some regimes where you lose the antiferromagnetic order. There, the question is there a tiny window between where you lose the antiferromagnetic order and where the large Fermi surface appears? There is a much smaller window there. And there, yeah, it could be. And we have made some predictions for that region in the superconducting phase, maybe. So I'll mention that next time.